Welcome back to the Deep Dive. Today, we're really getting into the weeds on the hardware that's basically defining this whole AI revolution. We're talking about high bandwidth memory, HBM.
Right. And it's crucial to understand this isn't just, faster RAM like you put in your gaming PC. This is completely different. It's specialized, it's vertically stacked silicon, and it's absolutely fundamental for everything driving AI right now.
Yeah, the LLMs, the big accelerators from NVIDIA, AMD, Google, they all need it.
Exactly. If you think about the core problem, the real bottleneck in AI today,
Yeah.
it's often not the raw compute power, the FLOPs. GPUs can theoretically scale almost indefinitely.
Right.
But getting the data to the compute, that's the hard part. Without the specialized memory, high capacity, super high throughput, your incredibly expensive compute engine just sits there waiting, starving.
That's the AI memory wall we keep hearing about.
That's it precisely. And HBM right now is basically the best, maybe the only technology that effectively bridges that gap, that hits the right balance.
Okay, so we've gathered quite a bit of material here. Sources looking at the tech, the manufacturing, the market dynamics. It's a real three-way battle shaping up between the big memory makers.
SK Hynix, Samsung, and Micron.
And we really want to focus today specifically on Micron technology. What's their position? What are the risks? What are the opportunities, especially if you're looking at this from an investment perspective?
Yeah, our mission today is to unpack why HBM is so different technically, look at the market shares, obviously, but also dive into Micron's recent moves. They've made this, surprising leapfrog in technology that we need to analyze.
And connect that all back to the investor. What are the strengths? What are the headwinds for Micron stock, specifically in the context of this HBM boom? Because the demand here seems different, not like the usual memory cycles.
It's explosive and it seems structurally different, yes. Less cyclical, perhaps, because it's so tied to this fundamental AI build-out.
Okay, let's start right there. The core problem. People usually think memory is about speed, right? Megahertz, and capacity, gigabytes.
Correct. Speed and density. But AI, especially large models, desperately needs a third dimension, bandwidth, just raw data throughput. Gigabytes per second.
And HBM somehow manages to deliver on all three fronts: capacity, bandwidth, and crucially for data centers, power efficiency.
Finds the optimum balance, yeah. Let's quickly break down the memory landscape. You've got SRAM on one extreme.
Super fast, like the L1 cache right on the processor.
Incredibly fast, lowest latency. But the density is terrible. It takes up a huge amount of silicon area, it's expensive, burns power, so you only use tiny amounts right next to the compute cores.
Then the other end is standard DRAM, like DDR5.
Right, conventional DDR DRAM, cheap, very dense, pretty power efficient. That's your main system memory. But the bandwidth, that's the killer. You just cannot physically move data fast enough off those DIMMs for what these AI models need. Hundreds of gigabytes per second. No way.
Which brings us back to HBM. How does it solve this?
It's a combination. Vertical stacking of multiple DRAM dies, one on top of the other. And crucially, this ultra-wide data bus connecting that stack to the processor. That's the magic.
So it balances density, bandwidth, and power in a way the others can't.
Exactly. It occupies the sweet spot. And because it does, it's become, non-negotiable. It's not optional anymore for high-end AI.
Every serious AI chip uses it. NVIDIA's H100s, their new Blackwell GB200, AMD's MI300 series, Google's TPUs.
All of them rely on HBM. And the trend, the roadmap across all these players is just relentless scaling. It's aggressive.
More stacks per chip, more layers in each stack, and faster generations of HBM itself. Like moving from HBM3 to HBM3E.
Yes, all three happening at once. And this scaling, this is where the money is for the memory vendors, including Micron. You just need to look at NVIDIA's roadmap. They really drive the market here.
Give us the numbers.
Okay, the A100, which was the workhorse just a couple of years ago, had 80 gigabytes of HBM2E.
Already a lot back then.
Seemed like a lot, yeah. The current flagship, the GB200, that's pushing 192 gigabytes of HBM3E per GPU.
More than double.
And the next generation, the projected Rubin Ultra analysts are already talking about potentially 1 terabyte, over 1,000 gigabytes per GPU.
Wow. That's a staggering increase. A 12x jump in just a few years.
Roughly, yeah. And that huge jump in memory content translates directly into the bill of materials, the bandman cost for every single one of these accelerators.
Meaning more revenue per chip sold, flows straight to the HBM suppliers.
Directly to SK Hynix, Samsung, and importantly for our discussion, Micron. This is why HBM commands such a massive price premium over regular DRAM. It's not just slightly better, it's fundamentally essential, and the demand curve is nearly vertical. It secures this high-margin, high-growth revenue stream.
Okay, let's spend some serious time now on the why. Why is HBM technically the king for this kind of throughput? You mentioned two things, the stacking and a wide bus.
Right, and they're inseparable. The wide bus is really the key differentiator. Think about a normal DDR memory channel, maybe 64 bits wide, running really fast, say 8, 10 gigabits per second per pin.
Trying to push speed.
Exactly. HBM takes the opposite approach. The bus is dramatically wider, typically 924 bits wide, but it runs each of those bits at a, let's say, more mediocre speed. Slower, more manageable signaling.
So instead of trying to blast data down a narrow pipe super fast, which causes all sorts of signal integrity and power headaches,
Right.
HBM opens up this massive 1,000-lane highway and moves data at a more relaxed pace, but 1,000 bits at a time.
Precisely. The total bandwidth per package ends up being vastly superior to anything else, even with those slower individual clock speeds. The magic is shrinking the distance. By stacking the memory right on top of or immediately next to the processor die, the electrical path becomes incredibly short.
Which avoids a lot of the problems you get sending signals across a motherboard.
Huge problems, yeah. But that proximity, that dense connection, creates its own challenge. How do you route over 1,000 connections between the HBM stack and the main chip in such a tiny space?
You can't use a regular circuit board, right?
Absolutely not. You need extreme routing density, and that mandates what's called 2.5D packaging. You need an intermediary layer, an interposer.
Like the silicon interposer in NVIDIA's CoWoS packaging.
Exactly like CoWoS, or sometimes a high-density organic substrate. This interposer sits between the main processor and the HBM stacks and provides the incredibly fine wiring needed to connect those 1,000-plus pins across that tiny gap.
Okay, and this physical layout leads directly to something our sources call the shoreline problem. Explain why this forces the vertical stacking.
Right, the shoreline analogy is quite good. Picture the main chip, the big processor die, the SoC. It leads to connect to the outside world, right? To the PCIe bus for the server, to the network interface.
The input-output, the I/O.
Exactly. That external I/O typically uses up 2 of the 4 edges of the chip package. Those edges are reserved for talking outwards.
Leaving only the other 2 edges available for internal connections, like memory. The shoreline.
Precisely. You've only got those 2 edges of the chip's footprint available to place your memory interface. Now imagine trying to lay out, say, 192 gigabytes of memory horizontally along just those 2 narrow shorelines.
The package would be enormous, impractical.
Totally impractical, physically impossible to manufacture, route, and cool effectively. So vertical stacking isn't just like a nice efficiency trick, it's a hard requirement to hit the necessary memory capacity targets within the physical constraints of a manufacturable package size.
Got it. And that technical necessity, the need for ever more capacity stacked vertically, feeds into this really interesting dynamic the sources mentioned, the memory Parkinson dynamic.
Ah, yes, I like that one. It's based on Parkinson's law, right? Work expands to fill the time available.
Exactly.
Well, the observation here is that neural network architectures, the AI models themselves, seem to expand relentlessly to fill whatever HBM capacity becomes available.
So developers don't get a new GPU with, say, a 92 GB of HBM and think, great, now we have plenty of headroom.
No. They immediately start designing or training a model that uses that 192 GB, pushes right up against the limit, and then they start complaining about the memory wall again.
So all the clever tricks they used just months before to squeeze a model into the older 80 GB limit, like aggressive quantization or checkpointing.
They often just get relaxed or thrown out the window as soon as more space appears. Then the cycle repeats. Push the model complexity, hit the new memory limit.
And the consequence of this perpetual cycle, for someone looking at Micron,
It's profound. It means that memory capacity and memory bandwidth remain a persistent, fundamental bottleneck, almost regardless of how fast the compute silicon gets. This guarantees, essentially, relentless demand growth for high-margin HBM for the foreseeable future. It decouples HBM demand, to some extent, from improvements in pure processing power.
Interesting. Okay, let's differentiate the usage a bit.
Right.
How is HBM used differently during AI training versus AI inference? Because inference seems to be where the memory pressure is really intense right now.
Inference is definitely where the bandwidth bottleneck is most acutely felt today, yes. The HBM in an inference server is doing 2 main things. First, holding the massive static weights of the model could be Hundreds of billions, even trillions of parameters, they just sit there.
And second,
Second, it holds the rapidly growing key value cache, the KV cache. This is the context, the history of the conversation, or the document being processed.
so the model can remember what was said earlier without recomputing everything.
Correct. And here's the key. Every single time the model generates the next word or token, which is the core loop of inference, the GPU has to read the relevant static weights, and it has to access and update the relevant parts of that entire KV cache history.
It sounds like a lot of data movement for just one word.
It is. This decode step is incredibly demanding on memory bandwidth. If the HBM can't shuttle those gigabytes back and forth fast enough, the expensive GPU cores just sit idle, waiting. Compute starved because of memory bandwidth.
And this KV cache problem is getting worse, isn't it? With models aiming for much longer context windows.
Exponentially worse. We're moving from models that remembered maybe a few pages of text to models designed for long horizon reasoning, analyzing entire books, managing complex multi-step tasks over long interactions.
Like OpenAI's deep research work. Context in the hundreds of thousands of tokens.
Exactly. And that blows up the KV cache size massively. When your KV cache starts demanding, 100 gigabytes or more per user, the service providers running these models are forced into really low batch sizes.
Meaning they can only serve one or maybe two users simultaneously on a very expensive GPU.
Right, which absolutely tanks the economics, the efficiency of the data center. And it drives this insatiable demand for GPUs with even bigger HBM stacks, like the 192 GB on Blackwell.
Okay, what about training then? Historically, training was seen as more compute-bound, right? Lots of matrix math.
Traditionally, yes. During standard supervised training, the HBM holds the weights, the intermediate results called activations, the gradients used for learning, and the optimizer statistics. It's busy, but the bottleneck was often the raw math performance.
That's changing.
It is evolving, yes. Our sources point out that a lot of cutting-edge work now involves sophisticated reinforcement learning, RL, particularly RLHF reinforcement, learning from human feedback and other complex fine-tuning methods.
Like improving model safety or specific capabilities.
Right. And a huge part of these new training paradigms actually involves running massive amounts of inference within the training loop itself.
Like using one powerful LLM to act as a judge to rate the outputs of the model being trained, or generating vast amounts of synthetic data.
Exactly, those kinds of things. You end up with these huge, constant inference workloads running side by side with the traditional training calculations. So modern training is starting to look a lot less like pure compute and more like high-intensity concurrent inference, which potentially spikes the HBM bandwidth and capacity pressure even in the training clusters. The lines are blurring, the memory wall is effectively getting higher and broader, hitting both training and inference. Good news for HBM demand overall.
Okay, with this relentless pressure, obviously people are looking for ways to mitigate it. We hear about KV cache offloading. What's that about?
Right. The idea is if the KV cache is getting too big for the expensive HBM, maybe you can move the less important or less frequently accessed parts of it to a cheaper, slower tier of memory.
Like spilling over into the main system DDR memory, or even onto fast NVMe SSDs.
Exactly. Frameworks like NVIDIA's Dynamo Distributed KV Cache Manager are designed to do this sort of tiered memory management. But, and this is absolutely crucial for investors watching Micron, this offloading is not cannibalizing HBM demand, it's complementary.
How so?
Because the HBM still holds the most critical, hottest data. Things like the initial system prompt, the very recent conversation history, the active sequence window, prefetch buffers, the stuff needed right now with the lowest possible latency.
It's like CPU caches, right? You still need the ultra-fast L1 cache, even if you have enormous amounts of slower main memory.
Perfect analogy. HBM remains essential for that immediate active working set. You can't offload everything without crippling performance.
And what about these newer agentic use cases? Models calling tools, accessing external data.
That actually increases the need for large, fast-working memory. If a model needs to quickly call an API, analyze a document it just retrieved, reason over that new information, and respond with low latency, it needs a large HBM capacity to hold all that temporary context efficiently.
So the takeaway from Micron investors seems pretty solid here. While techniques like offloading exist, they manage the excess demand. They don't fundamentally reduce the core requirement for ever larger, faster HBM stacks.
Correct. It might slightly moderate the slope of the demand curve in certain scenarios, but the overall trajectory for HBM remains strongly upward.
All right, let's shift gears completely. We've established the demand is intense, maybe even structural. Now, the supply side. This
Mhm.
is where the competitive dynamics for Micron really come into play, and it seems to hinge on some very specific, tricky manufacturing steps.
Absolutely. The sources are very clear. If you want to convert your factory capacity from making standard DRAM to making HBM, the main bottleneck, the limiting factor, is adding capacity for through silicon vs, TSVs.
Okay, explain TSVs. Why are they the bottleneck?
So in a normal DRAM chip, all the connections are on the surface. For HBM, because you're stacking chips vertically, you need to create electrical pathways through the silicon die itself to connect one layer to the next and ultimately down to the interposer. Those pathways are the TSVs.
By making them as hard.
It's a complex, multi-step process that's completely different from standard chip making. You have to etch these incredibly tiny, deep holes, or vias, into the silicon wafer. Then, and this is critical, you use deposition and plating techniques to perfectly fill those microscopic holes with copper, creating the vertical wires.
Great.
Then you have to flip the wafer over and grind the backside down, thinning it dramatically, sometimes to just tens of microns, to expose the other end of those copper TSVs. This thinning process itself is really challenging. You often need temporary bonding to support the fragile thinned wafer.
Wow. Yeah, that sounds nothing like making regular memory.
It's a whole added layer of manufacturing complexity, cost, and potential yield loss. And because it's the most complex new part of the process, a memory maker's ability to produce HBM is often quoted directly in terms of their TSV capacity. That's the real choke point.
And because it's this sophisticated stacked structure, a 3D integrated circuit, or 3D IC, the yields aren't as good as standard memory.
Nowhere near. You get yield loss both in the front end during TSV formation and then more yield loss in the back end during the delicate process of actually stacking these thin dies precisely on top of each other and packaging them.
Lower yield means higher cost per good die.
Exactly. That lower yield combined with the overwhelming demand is precisely why HBM commands that massive price premium we talked about. But here's the key for investors. Despite the challenges, the premium is so large that HBM is highly margin accretive.
Meaning Micron actually makes more profit margin on each HBM chip sold than on their standard DRAM chips.
Significantly more. So, even though it's harder to make, successfully ramping HBM production is boosting Micron's average selling prices, ASPs, and overall profitability substantially. It's a major positive driver for their financials, shifting them away from the pure commodity DRAM cycle.
Okay, so manufacturing is key, and this is where the competition gets really fierce, defined by proprietary packaging techniques. Let's break down the divide between the big three, SK Hynix, Samsung, and Micron.
Right. SK Hynix is the current market leader, especially in the latest HBM3E generation. Their big advantage is their proprietary packaging process using Nuar MUF.
Molded underfill.
Exactly. They co-developed this special epoxy molding compound with a materials company called NMSS. After stacking the dies, they inject this MIR MUF material, which flows into all the gaps. It acts as both the physical glue holding the stack together and as the primary path for heat to escape the stack.
And this gives them advantages.
Two main ones, according to the sources. First, it's apparently a higher throughput process compared to the alternative. Second, it offers potentially better thermal performance because the underfill material itself helps conduct heat away more effectively than just a thin film adhesive.
And crucially, this MRMUF process helps them manage die warpage, which is a huge problem with thin dies.
Yes, they seem to have a good handle on warpage using MUF, which allows them to mostly avoid using a slower, more complex bonding technique called thermal compression bonding, or TCB.
Okay, so that's Hynix. What about Micron and Samsung?
Micron and Samsung primarily use a different approach based on non-conductive film, NCF. They apply a thin adhesive film between each die before stacking. This NCF approach generally does rely on that slower TCB process.
So explain TCB and why it's slower or riskier.
Thermal compression bonding involves applying both heat and significant force to each die as it's placed onto the stack, melting tiny copper bumps to form the connections. Because you have to apply force and heat precisely for each layer, it's inherently a slower, more sequential process than just injecting MUF around the whole stack at once.
And potentially riskier.
Potentially, yes. Applying force to these incredibly thin, fragile dies increases the risk of cracking or damaging the delicate micro bumps that form the electrical connections. Lower yields, potentially.
So Hynix seems to have a manufacturing throughput and maybe thermal advantage with MRMUF, while Micron is using the potentially slower, maybe slightly riskier NCF-TCB method. That sounds like a disadvantage for Micron.
On the surface, yes. That difference in packaging speed and potentially thermal efficiency could be a significant factor in Hynix maintaining its lead in volume and time to market for the newest generations.
But Micron has found a different angle to compete on, right? Not the packaging material itself, but something deeper inside the stack.
Exactly. This is where Micron's story gets really interesting, and it's tied back to those TSVs we discussed. It's about the power distribution network, PDN, through the TSVs.
Okay, this is apparently Micron's big claimed advantage. Why is the PDN so critical?
Delivering clean, stable power up through that stack of maybe 8 or 12 active DRAM dies is incredibly challenging. DRAM operations, especially refresh cycles, draw sudden bursts of high current.
Right.
If your power delivery network formed by those TSVs isn't robust, the voltage can droop under load that's called IR drop. Voltage droops cause instability errors and generate excess heat. So the design of those power TSVs is proprietary and a major area for differentiation.
Hynix made improvements here too, right, for their HBM3E.
They did. They significantly increased the number of TSVs dedicated to power, reportedly almost 5x more, by adding them all around the periphery. This apparently cut their voltage drop by up to 75% for certain operations, a big improvement.
But Micron did something even more notable.
This is what the sources call Micron's surprising leapfrog. They successfully skipped the entire HBM3 generation, which Hynix and Samsung both produced, and jumped directly to an HBM3E product that is competitive, at least on paper, with Hynix's best.
And the consensus is this success came from focusing intently on the TSV design.
It seems so. Analysts believe Micron prioritized engineering a superior power distribution network from the ground up, focusing on the quality and efficiency of power delivery through those TSVs, perhaps even overhitting the absolute maximum initial data throughput.
And what's the payoff? What's the big claim Micron is making?
This is the headline number. Micron claims its HBM3E product consumes up to 30% less power than competitors' equivalent offerings, specifically because of this superior TSV and PDN design.
30%, that's huge in a data center context.
It's massive. Now, we absolutely have to stress, this is Micron's claim. It hasn't been independently verified publicly by hyperscalers who are notoriously secretive about benchmarks. But if it's true,
it's a game changer, right? Power and cooling are enormous operational costs for data centers running thousands of these power-hungry AI chips.
exactly, a 30% reduction in memory power per GPU doesn't just save electricity costs. It means less heat generated, which simplifies cooling, allows for denser racks, improves reliability. It hits the total cost of ownership TCO calculation directly.
So even if Hynix has a throughput advantage from MRMUF, Micron could potentially win deals based on this power efficiency claim.
That seems to be their strategic play. They're betting that for many hyperscale customers, especially as AI deployments scale massively, this TCO advantage driven by lower power and better thermals might be more valuable than having the absolute highest peak bandwidth number or the fastest manufacturing cycle.
It's a compelling argument, especially since we know HBM failures, often heat-related, are a major headache for data center operators. Better thermal stability could mean higher reliability.
That's a critical point we'll come back to. Lower power translates directly to lower heat, which should translate to better long-term reliability. In a 247 AI cluster, reliability is gold.
Okay, so a potential major strength for Micron there, albeit unverified. Let's look at the bigger picture risks now, starting with geopolitics. China.
Yeah, this is a significant shadow hanging over the market. Current U.S. export restrictions ban the sale of raw HBM stacks directly to China. However, chips containing HBM, like GPUs, can still be shipped if they fall below certain performance thresholds, FLOPS limits.
But China isn't just sitting back. They see HBM as strategic.
Absolutely not. They're reportedly planning something like $200 billion in state subsidies for their domestic semiconductor industry over the next few years, and a significant chunk of that is earmarked specifically for catching up in HBM.
And the main player there is CXMT, China's national DRAM champion.
Yes, and they are moving incredibly fast. Reports indicate they're aggressively stockpiling manufacturing equipment to get ahead of potential future export controls, hiring talent, and ramping capacity.
What are the concrete projections? This is critical for Micron investors.
Okay, the specific metric highlighted is this. CXMT is apparently targeting mass production for its first HBM product, an HBM2 8 high stack, sometime in the first half of 2025. That's soon.
Okay, HBM2 is older tech, but mass production is key.
Right. But here's the kicker. Their internal projections, according to supply chain sources, aim for their total TSV manufacturing capacity. Remember, that's the real bottleneck, to actually match Micron's total global TSV capacity by the end of 2025.
Wait, match Micron's capacity by the end of next year? That sounds incredibly aggressive. Is that realistic?
It's extremely aggressive, and whether they hit that exact timeline remains to be seen, but the ambition and the sheer scale of investment signal a very serious long-term competitive threat to Micron's global market share.
Even if CXMT starts with older HBM2, having that much capacity means they could potentially flood the market with lower-cost alternatives down the line, pressuring Micron's pricing, especially for slightly older generations.
Precisely. It could cap Micron's ability to sell off its own trailing-edge inventory profitably and erodes their overall market position over time, particularly if geopolitical tensions ease or loopholes are found in export controls. It's a major risk factor.
Okay, another scaling challenge. Layer counts. We need more capacity, so we need more layers per stack. HBM3E is hitting 12 high. What's the problem pushing higher?
It's purely physics and material science at this point. To stack more layers, say 16 or eventually even 32, within the package height limits set by the industry, JGDEX standards, you have to make each individual DRAM die incredibly thin.
And super thin silicon wafers are fragile.
Extremely fragile. They warp easily during processing, they're prone to cracking during handling and the bonding process. Basically, yields plummet as you try to go thinner and stack higher using current methods, costs skyrocket.
This is why everyone's been talking about hybrid bonding, right, as the solution.
Exactly. Hybrid bonding, or HB, is this advanced technique where you directly bond the copper pads on one die to the copper pads on the next without the solder micro bumps used today. This eliminates the height taken up by the bumps and the underfill gap,
Freeing up space to stack more layers within the same total height, or use thicker, more robust dies for the same layer count?
Correct. It's seen as the essential enabling technology for getting to 16 high stacks and beyond. However,
There's always a however with cutting-edge manufacturing.
always. Scaling hybrid bonding to high-volume production with good yields has proven to be, as the sources put it, extremely difficult and expensive. Particularly for complex high-layer stacks like HBM, the alignment requirements are incredibly precise, contamination control is critical. The industry keeps thinking HB is just around the corner, and then it gets pushed out again.
So where does that leave us now, especially regarding Micron?
Well, there was a very significant recent development. JDES, the standards body, officially relaxed the maximum allowed stack height for HBM packages. It used to be capped at 720 micrometers. They've now increased that limit slightly to 775 micrometers. It sounds tiny, just 55 microns difference.
But it has big implications.
Massive implications, because that extra 55 microns of headroom means that manufacturers can now likely achieve 16 high stacks using their existing proven bump-based bonding technologies like NCF-TCB or MRMUF, perhaps by using slightly thicker bumps or dies than previously thought possible.
So the immediate, desperate need to perfect hybrid bonding just got lessened, delayed.
Exactly. It kicks the can down the road. It suggests that the current bump-based tech has a longer lifespan, particularly for hitting that next major capacity target, 16 high, than maybe the industry anticipated 6 months ago.
And how does this play out competitively for Micron?
It's arguably a near-term benefit for Micron and Hynix. It reduces the immediate pressure to pour massive capital into scaling up risky, low-yield hybrid bonding lines. They can likely extend their current, relatively mature NCF-TCB process for another generation or iteration.
Whereas Samsung
has been the most vocal proponent of moving quickly to hybrid bonding. Our sources characterize this as typical Samsung setting aggressive technical goals that sometimes outrun their execution capabilities. So this JDEC relaxation might actually be a slight setback for Samsung's strategy if they were betting heavily on an earlier HB transition.
Interesting. So for Micron investors, this delay in the HB transition is actually a positive. It lowers near-term CapEx risk and extends the value of their current manufacturing know-how.
That seems to be the implication, yes. It gives their current tech, including that potentially power-efficient TSV design within the NCF-TCB framework, a longer runway to generate returns before the next huge manufacturing paradigm shift is absolutely required.
Okay, one more major event to cover. The Hanmi supply chain shock from early 2024. This really highlighted dependencies.
Yeah, this was a big one, centered around those critical bonding tools we mentioned.
The thermal compression bonders needed for stacking the guys.
Precisely. These are highly sophisticated machines needing sub-micron accuracy. A Korean company, Hanmi Semiconductor, had achieved something close to a monopoly supplying these TC bonders, especially to the market leader, SK Hynix.
Okay.
But Hynix, likely wanting to diversify its suppliers and gain some negotiating leverage, placed a very large order for bonders with a competing Korean equipment maker, Hanwha Precision Machinery.
And Hanmi didn't like that.
Apparently not. In what seems like a retaliatory move, in April 2024, Hanmi reportedly pulled all of its field service engineers out of SK Hynix's fabrication plants.
Wow, no service means the tools eventually stop running.
Exactly.
Yeah.
It threatened to grind Hynix's HBM production, particularly the cutting-edge HBM3E needed for NVIDIA's Blackwell, to a halt within months. It sent shockwaves through the entire AI accelerator supply chain.
A major crisis averted eventually, I assume.
Yes, the situation was resolved relatively quickly, but the key takeaway for our discussion, explicitly noted in the sources, was what happened during that period of uncertainty.
Which was?
It became clear that Micron and Samsung could not quickly step in to fill the massive capacity void if SK Hynix production actually went offline.
Ouch. So, despite Micron's technical progress, they just didn't have the scaled-up volume capacity ready to meet that kind of sudden surge in demand for the highest-end product.
That's what the incident strongly suggested. It underscored the reality that SK Hynix currently holds a significant lead in volume production capability and supply chain readiness for the latest HBM generation, even if Micron has potentially closed the gap on performance specs like power efficiency. Micron still trails on sheer scale and throughput.
A critical point for investors weighting market share potential versus technical claims.
Absolutely. Technical wins are great, but you need the factory capacity to deliver at scale.
Okay, let's pull all this together now. Section 4, investor synthesis. We need to balance Micron's strengths against these risks and headwinds. Let's start with the clear positives for a Micron investor.
Strength number one has to be the margin profile. HBM is fundamentally changing Micron's profitability. It's highly margin accretive compared to their traditional DRAM business. This means more cash flow, more funding for R&D, and potentially a structural re-rating of the stock away from just being a cyclical memory play.
Right. The second big strength is that technological leapfrog we discussed, successfully skipping HBM3, focusing on the PDN and TSVs.
And achieving that claimed 30% power efficiency advantage. Again, if verified, this isn't just a minor spec bump, it's a potentially decisive TCO advantage targeting the biggest operational pain point for hyperscalers: power and heat. It's a very strategic technical win.
And third, that near-term market dynamic around hybrid bonding.
Yes, the JADEKI height relaxation effectively delays the need for massive investment in risky HB technology. It gives Micron more time to capitalize on its current NCF-TCB process and that potential power advantage, reducing near-term capex pressure and extending the runway for their current generation.
Okay, those are compelling strengths. Now let's be clear about the risks and headwinds facing Micron investors. First, that packaging disadvantage.
Right. They're still primarily using NCF-TCB, which the consensus suggests is less productive, potentially slower throughput, and maybe less thermally efficient than SK Hynix's established MRMUF process. This puts a potential ceiling on how quickly Micron can ramp volume and potentially keeps them a step behind Hynix on pure manufacturing scale.
And that leads directly to the second risk, the demonstrated capacity bottleneck.
Yeah, the Hanmi incident starkly illustrated this. Micron wasn't positioned to rapidly absorb a massive surge in demand had Hynix faltered. This suggests they still trail significantly in overall volume readiness and supply chain agility for the very latest HBM3E products. Customers needing huge volumes quickly might still default to Hynix.
Third, the geopolitical thundercloud, China and CXMT.
It's a major long-term threat. CXMT's stated goal of matching Micron's TSV capacity by late 2025, backed by massive state funding, cannot be ignored. Even if they start with older HBM tech, that sheer volume hitting the market eventually will pressure prices and Micron's global market share, especially in segments that are slightly less performance sensitive.
And finally, the strategic risk around innovation, specifically hybrid bonding again.
Right. While being cautious on HB is a benefit now, Micron has been described as far quieter on their HB roadmap compared to Samsung's aggressive pronouncements. If Samsung or even Hynix does achieve a breakthrough in scaling HB cost-effectively for future HBM4 or HBM4E,
Micron could suddenly find itself significantly behind the curve on the next major technological transition, forced into a very expensive and rushed catch-up game. Their current caution could become a future liability.
it's a delicate balancing act for them.
Absolutely. Okay, let's wrap this deep dive up. It's been incredibly detailed, looking at the silicon heart of AI and what it means for Micron. The core finding seems undeniable. The memory wall isn't going away. That memory Parkinson dynamic ensures HBM demand is structural. It's non-negotiable for AI's future growth.
Right. And that provides a very strong baseline demand for Micron's high-margin HBM products. They've also clearly engineered a significant technical win with their focus on TSV power delivery. That 30% claim is potentially huge if it pans out in real-world TCO.
But they're operating with some structural handicaps. The NCF TCD packaging might limit their throughput compared to Hynix's MR-MUF. Their ability to scale volume rapidly seems less developed than the leaders. And looming over everything is that aggressive, state-funded capacity expansion from CXMT in China.
So for investors, the story really boils down to execution. Can Micron translate that potential power efficiency advantage into verified customer wins and tangible market share gains, despite Hynix's manufacturing lead and the growing threat from China? That's the multi-billion-dollar question.
And that leads us perfectly into the final provocative thought we want to leave you, the listener, with, something to mull over.
We mentioned earlier that hyperscalers report HBM failures often related to heat and stress as the #1 cause of premature GPU failures in their massive data centers. We also know that DRAM fundamentally does not like heat. It impacts performance and longevity.
Okay.
So consider Micron's unverified claim of 30% lower power consumption. Could this represent more than just an operational cost saving on the electricity bill? Could lower power, leading to lower operating temperatures and less thermal stress, actually be the ultimate moat for durability and reliability in these 247 AI factories?
Meaning, if Micron's HBM proves to be significantly more reliable over the long haul because it runs cooler.
Could that become its most valuable selling proposition? Perhaps even outweighing small deficits in peak bandwidth or manufacturing speed, especially as AI infrastructure matures and uptime becomes paramount. If the market eventually prioritizes longevity above all else, Micron's intense focus on that TSV power network might just be the smartest bet they've made.
A potential long-term reliability advantage hidden within an efficiency claim. Definitely something to think about as you watch this space evolve.